असतो मा सद्गमय तमसो मा ज्योतिर्गमय मृत्योर्मा अमृतंगमय। ॐ शान्ति शान्ति शान्तिः।
Namaste, my dear young friends. In today's video, we learn about position time graphs for accelerated motion and retarded motion. Say, accelerated motion means, as we learnt in previous videos, the velocity goes on increasing and the distances covered goes on increasing. In the retarded motion means the velocity goes on decreasing, distances covered goes on decreasing. So keeping these things in mind, we want to draw graphs for position time graphs for uniformly accelerated motion and uniformly decelerated motion. First, we take up position time graph, or what we call as xt graph, for uniformly accelerated motion. Observe carefully. xt graph for uniformly accelerated motion. Uniformly accelerated motion. So what we do or how we do? As usual, first of all, we must get a mental picture, or also we can create a tabulation. And then you can write. But in the exams, they may ask you typical graphs without scale or anything. You can write the typical curve like that. Okay, now, first of all, I write the time and position. Say for uniformly accelerated motion, as we all know, as time increases, the distances covered should go on increasing because the velocity goes on increasing. Observe, we create a mental picture once again. What we learnt, imagination. Say, an object is here on straight line. It's moving. In the t equals 0, it is here. At t equals 1 second, say, a is the acceleration. At t equals 1 second, say, let me write here. T equals 1 second, observe the distance covered less. In the t equals 2 seconds, it is still more. We have written it, we have learnt it. And then, in one acceleration video, I have shown this. Say t equals 3 seconds, it is still more. Observe the distances covered goes on increasing. If you want to write the positions, you write x0. You may write it as x1. Simply for the sake of clarity, I am writing x4. And this is x9, 9 meters. So if you draw a graph of this, observe 0 to 1. So 0 to 1 second, it covered 1 meter. 1 second to 2 second, it covered 1 to 4, that is 3 meters. So 2 second to 3 second, it covered 4 to 9, that is 5 meters. Therefore, if I draw a graph, position on y-axis, time on x-axis. So we write 1, or else we do like this. 1, 2, 3, 4, 5, 6. Let me extend it till 7, 8, 9. I write x equals 1 here. 9 is here. Here 1 second, 2 second, 3 second, 4 second, 5 second, like that. 1, 2, 3, 4, 5. Now, so observe, we draw a graph. If we draw a graph, what we get is like this. First, 0 second, 0 second, it is here. And then, for 1 second, x equals 1, somewhere here. For 2 second, x equals 4. So, 2 second, x equals 4 somewhere here at this point. And then for 3 seconds x equals 9. Observe somewhere here. I take. So graph will be like this. Graph will be like this. So we just have written, say, a graph without any scale or anything. Simply for the sake of clarity, I have written this. So it goes on. It clearly shows in 1 second this is the distance, in 2 seconds this is the distance, like that. So this is the graph for uniformly accelerated motion. In the same manner, we can write for uniformly decelerated motion. And there the distances goes on decreasing and we write up to the object come to rest. So now I continue with the other things. Here also, if you want to complete this 0 tabular column, and 1 second 1 meter, 2 second 4 meter, x in meters, t in second, 3 second, say 9 meters, it goes like this. That's what I marked. Now we go for uniformly retarded motion or decelerated motion, where the velocity goes on decreasing and the distance covered also goes on decreasing. We write that. Say, once we have done it, we use the same tabular column, but graphs are different. I write once again completely. Just observe. For uniformly retarded motion, we write, we learn. Uniformly retarded motion. That means deceleration. Uniformly retarded motion. Here, the situation is like this. If you have a straight path, an object is moving at velocity v at t equals 0 second, at t equals 0 second, it is moving, and we take its position as 0 there. Where we start, say for example, when we are moving on a car or any vehicle, when the brakes applied, that from that point or from that instant we start counting the time. That's why t is 0, and we start counting the distance also. That's why x 0. After 1 second, t equals 1 second, it might have covered 3 meters. Say after 2 seconds, it might be at 5 meters. Observe, here to here 3 meter, here to here 2 meter. In the coming thing, it might be still less, t equals say 3 seconds. Then at t equals 4 seconds, say we imagine, x is say around 5.5 meters and it comes to rest, v equals 0. This is the situation. Now, if I draw a graph, here also I draw, the scales are simply, the numbers are simply to tell you how they are. They may not follow any proper thing. I have not calculated anything, only to show you. Calculated values we see in the later videos when we take up the equations of motion and other things. So 0, 0, 1, 3 meter, 2 for 2 seconds, up to 2 seconds, it is 3 plus 2, 5 meter position, and then for 3, it is 5.5 meter position. 5.5 meter position. So for 1 second, 3 meter position. For 2 seconds, it is 5 meter position. 3 seconds come to rest at 5.5. If we draw a graph again, observe carefully. If we draw a graph x versus t, we write 0, 1, 2, 3. And then here we start with 0 position, 1, 2, 3, 4, 5, 6. So 5.5 somewhere here. Now for 0, 0, the position is 0. Then for 1 second, position is 3 meters somewhere here. For 2 seconds, position is 5 meter, say somewhere here. For 3 seconds, it is 5.5. So finally, we get a graph like this. After that, it comes to rest, so it becomes parallel to the x-axis. This is the graph of retarded motion, position time graph for retarded motion. So there I conclude this video.